In the last video, towards the end, I had a table that showed the energy released per mole of carbon for complete oxidation or incomplete oxidation, but you get either CO2 or carbon monoxide. And so as you can see that the energy change is smaller, the energy released is smaller if the oxidation is incomplete. And the energy per mole of carbon also goes down as the number of carbon increases. So you may get a higher amount of energy, but the energy per mole of carbon actually goes down all the way from methane and go from methane. So what we're going to do next is to do the same type of writing of the equation, balancing the equation, calculating the enthalpy change. This time you notice this was propane, C3H8, 3 carbons, 8 hydrogens with oxidation oxidation, giving you carbon dioxide and water. The change in enthalpy, you can calculate it. You need to pay attention to these because you're going to have some quizzes, homework problem where I'll ask you to do these calculations for, say, a mixture of these hydrocarbons. So you may be able to go back through these videos and figure out how to do these using the tables. If you do that for butane, you get a number of minus 2678.53 kg per mole and so forth. The details of the calculations are on these slides. So for heptane, again, similarly, you get a number of 4501.21 kilojoules per mole. And so in this table, there's a summary. It says if you have methane, you need 2 molecules per mole of methane, 2 moles of oxygen per mole of methane, and you get the energy released per mole of carbon over here. As you notice, as the number of carbons goes up, your oxygen requirements go up too, as you would expect. So clearly, if you're going to be burning anything other than methane, you're going to need more oxygen to burn it, right? Even though the energy released per mole of oxygen actually goes down as you go from methane to ethane, butane, and so forth, right? So the one key lesson is if our carbons are oxidized at the highest state possible, the heat released is the highest per mole of carbon. So you also need the most amount of oxygen for burning the methane. So keep in mind these energy calculations are assuming complete and total combustion or incomplete combustion to CO, and we are assuming that the entire fuel is burned essentially in the chamber. Clearly, if only half of the fuel is burned, the energy content is going to be approximately half of what you get, and so forth. Okay, so what we've done next is a similar thing. What if you were to look at incomplete combustion for, say, methane, ethane, as we did in the previous video, and these are the balanced equations. Check them, make sure they're balanced. And again, a summary. It says if you have methane, for example, for these incomplete combustion, you need 1.5 moles of oxygen. For ethane, you need 2.5 moles, so on and so forth. So that number goes up, and the energy released per mole goes down as you go from methane to higher hydrocarbons. Okay, so you can imagine you can write balanced equations for gasoline, but that assumes you know what gasoline is made of. Gasoline is a blend of C7s through C11s approximately. That is C7 with hydrogens and C11s with hydrogens, for example. It's really difficult to define the exact composition of gasoline because it'll have a variety of different linear hydrocarbons, branch hydrocarbons, aromatic hydrocarbons, and so forth. But fundamentally carbon and hydrogen compounds. Same thing with diesel, except diesels have a slightly higher molecular weights, for example, 12s or 15s or 17s, so on and so forth, right? So you can imagine if you know the exact composition of gasoline and diesel, you can write the equation for each of those common compounds and calculate what the energy released should be. And so in principle, it should be possible to calculate what the theoretical amount of energy you should get from a gasoline or diesel whose composition you know. And we might run through some of that as we move forward. So far, we're talking about gasoline and diesel. Are there other things that can burn, can oxidize with oxygen, as we talked about? The answer is, of course, yes. So it's like, well, imagine if I have C2H5OH, you might recognize what this molecule is. You can imagine mixing with oxygen somehow and making it, quote unquote, burn. And you can calculate and you get a number. That in fact, you do get energy released when, in this case, ethanol is actually oxidized, and you get energy release. You can calculate the energy release per molecule of carbon, per mole of carbon for complete or incomplete combustion, and the energy release per mole is still less than that of methane, but you can imagine that this is something which will actually burn, and you can imagine using it as a fuel, right? So that brings us to a question that says, well, can you use anything as fuel? Can you use wood as fuel in a car? Actually, you can. If there is a way in which you can burn wood, confine the gases in a chamber and make the pistons move. You might have seen some old pictures of the people actually using wood. There are some wood burning automobiles, as it were. So you can, in principle, though it's not going to be as efficient as you can imagine. So anything plus oxygen, you can imagine getting some energy out of it, right? The one thing I'll mention is that one of the problems, if you will, with the internal combustion engine is that while it creates carbon dioxide or carbon monoxide and creates the energy, because of the high temperature in that confined region, certain oxides are also formed that are highly undesirable, in particular nitrogen oxides. And so while you may actually, there may be good reason to burn them at very high temperatures to create the maximum energy, you'll have to figure out a way to eliminate some of the nasty oxides that are actually formed. And so designing a combustion chamber for the automobile is not tricky. How do you get maximum energy while minimizing some of the bad oxides that also, also form? So they are undesirable. We had to figure out a way to eliminate them. So what we've done so far is to introduce the concept of a balanced chemical reaction. From that, calculating the energy released per mole of methane or per mole of butane. And it looks like, for example, the most efficient fuel is actually methane, because the amount of energy released per mole of methane for total combustion is the highest number that we can find, right? So it appears as if all we should be doing is using natural gas as part of a fuel and not gasoline. So think about that. I mean, is that what we should be doing? I mean, why are we using gasoline if natural gas in fact gets much more efficient? And there are some reasons for that, and we will explore that as we move.